Okay, I think we will start with the webinar today. Okay, I would like to ask everyone, please, to turn off the microphones and also the cameras. And during the presentation, we will have some time for questions and at the end of the presentation, so you will be able to, to ask your questions to Emanuele. So it is my pleasure to introduce you Emanuele Bugliarello. Sorry, I have some problems with the network, so I will be very brief. Okay, and I was saying that Emanuele has been very influential. He has been working in very well-known vision language models like PalyGemma and also benchmarks like iGlue. And he was also one of the authors of a very influential paper, Language Modeling with Pixels, where they introduced a radically new paradigm for tokenization in language models. And today, Emanuele will talk about vision language models, but from the multilingual and multicultural point of view. So whenever you want, Emanuele, you can start with your talk.
Yeah, thank you very much for inviting me and for the introduction. Yes, I will be talking about some work we've been doing towards making multimodal models work better and be more inclusive with respect to cultures and populations from the world. So I think everybody's realized by now that AI is making a lot of progress, and the progress just goes quicker and quicker. So this is a graph from Dawe and colleagues, where you can see how long it took a model to reach human performance across different tasks. And it's clear that the more we go in time, the faster the models are at achieving this sort of performance. And you can also see on how LLMs perform on LMCs, this popular benchmark for evaluating large language models. And we can see this clear trend. These models are getting better and better, not only from proprietary LLMs like Gemini and ChatGPT, but also open source ones, which I think is a great place to be in terms of research in this space. And these language models over the last couple of years have expanded in scope. So we went from tasks that were specifically for language, and now we use this model to tackle different types of tasks related to biology, to geography, mathematics, physics, and so on. And what I think this is really, really exciting in terms of progress, in terms of achieving AI, we need to make sure that these models work for everyone. And this is especially true because more and more people are relying on these models in their everyday life, and the decisions that this model outputs it might influence a lot how people are feeling about these models, and some may even have some harmful result. So here's, for instance, there was a case a few years ago where a model for facial recognition led to a false arrest of a person of color. And this was the result of the model being performing worse in identifying people of color. Another case is using these AI models for hiring strategies. So sometimes you use these models to filter resumes. And there was a case in 2018 where the model was biased in terms of downgrading resumes that contained words like women's, so women's club or women's math club. Another case of potential harm that these models have experienced before is this of reinforcing stereotypes. So when the first AI-generated text-to-image models came out, we saw that they were like reinforcing some harmful stereotypes, such as identifying men as CEOs or men as doctors and women as nurses. And even more, as we move towards these generative models, for instance, models that can generate videos that look more and more realistic, these can be used to spread misinformation, such as fake news, and even affect political propaganda. So we have powerful models that can do a lot of interesting tasks, but the way they can be used can also be very harmful for the population. While there are many types of harms that these models can cause, what I want to talk today is more a broad type of problem, which is that of having AI that works for different culture. Now, the term culture itself is a very complex construct that can depend on several things, from such as the language you speak or the country or the region you're from. And in the context of this talk, I'll mostly be talking about regional culture. So you can think of this as your country, or as your region if your country has very different facets. And when we work with AI and like NLP models like LLMs, I think it's also interesting and it's also important to remember that we're not just handling language per se, but NLP is a task that sort of on a research area that is actually for people. So we don't just use language as a construct. We use language to communicate with each other, and this communication is very much modeled by the social relation and context and norms that are typical of our environment. And now even some things like common sense, some of the things in common sense, for instance, are at high level universal, while others very much depend on your culture. So I think it's very important that these models, they really recognize that language and culture are intertwined with each other. And when myself have been working a lot on multimodal AIs, and in this aspect, there are even greater challenges that these models face. So in the context of communication, we use a lot of nonverbal signals when we communicate with each other. And even some like typical gestures like crossing your fingers that are used to wish good luck in Western countries might have very different connotations across the other countries in the world, such as here in Vietnam. So I think it's very important that we acknowledge that this is possible, and we need to make sure that these models are aware of these potential harms that they cause to the populations where they're deployed. And besides this, it's also like harder to fix these issues when we work in the multimodal space, because we go directly from a discrete case, such as language, to a very continuous space where we have images, video, speech, as well as text. And so like the point I want to make today is that cultural understanding is essential for deploying these models at scale and make sure that people from different cultures feel comfortable using these models, and they don't cause bad reactions to the population. And so today I'm going to talk about how we can try to tackle and what are the challenges in tackling these problems. We're going to look at the three different aspects: evaluation, training, and generation. So the talk is mostly going to focus on work that I've been involved in, but also I'm going to touch upon some recent work that I think is interesting and exciting in this direction. There's a lot of work going on in the community, so the talk itself is going to be like a biased version of what is available in the literatures. And so I encourage you to check out more papers if this is something that you find interesting as well. And feel free, I don't know, if you want to ask questions at any time during the talk or after each of these sections. But before delving into that, I want to just make sure we have some sort of common ground with respect to what we mean by multimodality. So as a very simple working definition, we define multimodal models as models that are able to process information from two or more modalities. These can be models that accept both image and text, or speech and video, or text, speech, and video, and so on. And in this talk, essentially, whenever I talk about multimodal, I will be talking about image-text models. So these are models that process jointly image and text modalities. In the community, there have been several approaches towards building general-purpose multimodal models, and these can be categorized into three different types. So we have discriminative cross-encoding models. These are embedding models that process both modalities together. Then we have dual encoder models. These are also encoders that are processing both modalities, but with two different modules that don't talk to each other. And finally, we have probably what is nowadays the most common type of model. These are generative visual prefix models, where we use a language model and we prefix some visual input through some sort of layer that connects them. So cross-encoding models, models that were deployed, started being developed from 2019 as a response to make a popular model, at the time, BERT, visually grounded. There have been different types of development and models for this type of family of models, and this could be categorized into two different families. The first one is single stream models, which are models that simply concatenate language and image tokens into a single transformer that processes the two modalities jointly. The second family is that of dual stream models. These are models that operate at different layers with different type of intermodal and intramodal connections. So you might have some layers where image tokens only attend to image tokens and text tokens only attend to text tokens, and then other layers where image tokens only attend to text tokens, and all of the possible combinations that you can think of. Back in 2021, we did a sort of meta-analysis of these type of models, and we found that under control conditions, these models perform similarly to each other. So this sort of difference in architectures is not really prevailed in a control study. Another type of models that is becoming more and more popular are these dual encoder models. These models have two separate modules, a language encoder and a vision encoder. And these are very useful in terms of having a high sample efficiency. These models are faster to run at inference time because you don't have cross attention over both modalities. So the sequence length is usually shorter. They're also faster to train because they require less memory on your accelerator, which allows you to scale up more also the batch size and therefore train faster. These models were initially popularized by Clip from OpenAI, which was trained to maximize the similarity between image and text embedding that correspond to each other, such as here I1 and T1, while minimizing the similarity with all the other pairs. One issue with this model is that you require a really large batch size in order to learn useful representations. And so in 2023, another model was proposed called SIGLEAP, which moved from this softmax in the objective to a sigmoid classification task, which allowed the model to be trained on a much smaller batch size while achieving the same performance. And a few weeks ago, a new version of SIGLEAP called SIGLEAP 2 has been released, and it also includes more fine-grained objectives. So if you're looking for models in this domain, I invite you to check it out. And finally, we have visual prefix models. So these are models that basically try to leverage the representations that are learned into modality-specific pre-training. So you can pre-train your vision encoder, you can pre-train your language model, and then these models just try to concatenate the two representations together in order to achieve a single unified model. Last year, we released two models called PalyGemma and PalyGemma 2, which are a type of an instance of this sort of family of models, where we take a SIGLEAP image encoder and then we attach it to a Gemma or Gemma 2 language model. The model is trained in 3 stages. So first of all, we have multimodal end-to-end training at low resolution. This makes easier to scale up the pre-training. Then we increase the resolution and continue training. And at the end, we release these checkpoints that can be easily fine-tuned on different tasks. The The great effect of this model is that this model can be easily adapted to a number of tasks that are relevant in the visual language community, such as visual question answering, optical character recognition, object detection, and so on. And it's currently what most of the VLMs nowadays look like. Right, so this was like a brief intro, so let's get started talking about more evaluation of multicultural models. So if you look at the data that we use nowadays to train multimodal models, it comes mostly in English. And with some exceptions, a few Indo-European languages like German and French, as well as some high-resource languages like Chinese and Japanese. So if you're interested in having like a model that understands your language, you might think that we could just translate the data that we have available in English in our target model, in our target language. But here's an example from Miltenberg and colleagues that shows why this is not necessarily a good approach. So in this photo here, an American speaker described it as an unusual looking vehicle is parked on the street. However, this picture was taken in the Netherlands, and if a Dutch person were to describe this, they would refer to this object as a street organ. So if you were to just translate from English into Dutch with a machine, like a machine translation model, then we would carry on the bias that the original American annotator had in describing the picture. But language is only one side of the coin when we talk about image text models, and even images that we use nowadays to train and evaluate most of our models have a very skewed distribution in terms of geographical representativeness. So here's an example from ImageNet, which is a very influential data set in the computer vision community. And we can see that most of the images come from the Western world. And so essentially, back in 2021, when we started this study, we realized that these models can only be evaluated and trained on a very narrow linguistic and cultural domain. And at the time, there was no real way to assess the abilities of these models to comprehend concepts across the entire world. And so the way that these data sets are vastly used for training and evaluating multimodal models are based on the WordNet concepts that are in English. So WordNet is a lexical database, and you can have this sort of hierarchy about concepts, such as in the example here from canine, you go to dog, and then you can have instances like husky. And so if you want to make data sets that are available for all the countries, we need to make sure that the concepts that we use to train and evaluate these models are actually representative of multiple countries. So we did a first study where we tried to estimate how cross-lingual the concepts of ImageNet are by using Wikipedia as a proxy. So we started from a concept in the ImageNet dataset, and we manually mapped it into its English Wikipedia page. And then from here, we could see which other languages have the same concept in Wikipedia. What we found is that most of the concepts that are in ImageNet are only available in 30 or fewer languages, while only a few concepts are universal. By that, I mean concepts that are available across 100 or more languages. And so we proposed a new benchmark, a new dataset called MaRVL, which stands for Multicultural Reasoning or Revisional Language, where we collected data for 5 typologically diverse languages. The way we collect data was independent from each language, and the images that we collected were to be representative of how people from that given culture usually see the concept in action. So here's an example for the concept of basketball, which is a concept that was shared across all the languages we collected data for. And you can visually see like the difference in the image connotations that we have in this in our data set. The task that we built this dataset for is that of visual reasoning following the NLVR2 approach. So here a data point consists of 2 images as well as a sentence. And the task is that of binary classification, where we want to predict whether the sentence does apply to both images or not. The way we collected this dataset was through a novel native speaker-driven protocol. So here we really rely on native speakers to make sure that this dataset is of high quality and representative of the cultures. So after identifying our 5 diverse languages, we asked human raters to collect concepts, then select images for these concepts, and finally annotate the dataset for the task. So the first step was this of selecting the concept. And here we started from a number of categories extracted from the Intercontinental Dictionary series, categories such as sport or food or buildings or clothes. And then we asked native speakers to tell us what are real instances that are relevant for their culture. So for instance, here, Turkish speaker told us that tennis is a popular sport in their country, in their culture. We then selected the top concepts per language. And when we double checked with their availability in WordNet, we found that roughly 20% of the concepts that we collected in this phase are not actually available on WordNet. So what this means is that models that have been trained on these standard datasets might have never seen some of these concepts during training. The second phase was that of image collection, where again, we asked native speakers to find images that are representative of the concept in their everyday life. And we also asked for more requirements that follow this NLBR2 task, such as having multiple instances of the concept or seeing the concept interacting with other objects. And finally, we again follow the NLBR2 protocol to describe pairs of images in a way that two pairs of images can be described with the same sentence and two pairs cannot. We do this iteratively to make sure that the final data set is of high quality, as indicated here by a Flace kappa coefficient of 93%. So yeah, here's like some of the examples that we collected, and I hope you had lunch, otherwise this might make you very hungry. When we then trained two multilingual models, here MUniter and XUniter, we saw that these models trained multilingual and multimodal data achieved similar performance as English-only models on the English dataset. However, when we evaluate these models zero-shot into the languages in MaRVL, we found a very big drop in performance from 15 to 20% absolute accuracy points. And here, some of the models even perform near random performance for this binary classification task, which is 50%. We got a lot of positive feedback from this first study. And so we continued on this topic by trying to create a benchmark that goes beyond the visual reasoning task and the 5 languages we had collected before. So what we did here was to construct a new benchmark called IGLU, which stands for Image Grounded Language Understanding Evaluation, where we identify 4 tasks that are typical in multimodal setups, such as NLI, question answering, and image text retrieval on top of reasoning. And then annotated these with multilingual captions and questions. In this case, we didn't really focus on having images that are culturally relevant, but our scope was more towards having a more representative set of languages that we could evaluate multimodal models on. And so these are some of the results that we obtained back in 2022 with the state-of-the-art models at that time. And we saw there was a huge gap between English-only performance and the average performance across different languages. Fast forward to 2024, we still see that current models do perform better than they did 2 years ago, but there's still a significant gap between English performance and multilingual, multicultural performance. Moreover, one of the interesting findings, in my opinion, that we had in this IGLU paper at that time was this inability to make few-shot transfer work. So in IGLU, on top of evaluation data, we also collected few-shot examples for each of the tasks. And these few-shot examples have been shown to be very effective in text-only tasks when we wanted to adapt an English-only model to a multilingual one. So in this case, for multimodal models, we found that this doesn't really apply, and that a few examples in the target language doesn't really help boosting performance. So here in the x-axis, you can see the number of few-shot examples that we used to train the models after being trained on English data. And then on the y-axis, you see the accuracy. And in our paper, we also show that if you have thousands of examples, then this model can catch up. But it's interesting that few shot examples are still very hard for these models. And besides our work on multilingual and multicultural dataset, there is an explosion of work in benchmarking and datasets in the last couple of years. So I'm going to mention two of the papers and datasets that I liked. The first one is called CBQA, which is a culturally nuanced BQA benchmark that spans over 30 languages. Here, the dataset consists of roughly 10,000 questions and answers, and that are covering 10 different categories that are available in both English and the native language. The way that the authors collected this dataset was through a participatory effort, where they asked anyone interested in the task to contribute 100 or plus validated question-answer pairs, and then become co-authors for this work. So I think this is like a very nice way to reach multiple people in the community, especially those from low resource and countries. And another dataset that is actually going to be presented at ICLEAR this year is called Pangea Instruct, which is an instruction multimodal dataset in 39 languages collected by CMU. And here, the authors collect data multilingually and image text data multilingually across different number of tasks. So you have document QA or chart QA or captioning or domain-specific examples such as medical domain and so on. I think one interesting finding from this paper was that English data is still very valuable to learn how to move from English only understanding to multilingual understanding. And specifically, the authors show that having this ratio of 40 to 60%, where 40% of English data is used, is actually helpful to help with this cross-lingual transfer. Moreover, besides data sets, there are multilingual and multicultural. There's also a trend of more and more data sets that are in English, but they can still capture different cultural elements across different countries. One example of this is Cultural BQA, which was presented at EMNLP last year, where different from MaRVL, they have roughly 44% of the questions about intangible aspects of culture, such as questions about rituals and tradition. And they see in this paper that there's a performance gap between proprietary and open source models, and that multilinguality, so training these models multilingually, doesn't necessarily help fix multicultural understanding. And finally, we also have, there's also like one recent dataset from this year called Culture Birth, where unlike previous efforts done more from the human-based approach, this really tries to scale up the amount of data that can be collected in a multilingual, multicultural way by including data from over 180 regions, and that covers a lot of concepts and different tasks. So we have image recognition, scene reasoning, as well as cultural knowledge. They find again that there's better performance in Western culture, as well as lower performance, especially in history and landmarks. And again, like previous work, finds that proprietary models perform much better than open source ones. Okay, so that was the first part of the talk. Basically saw that multicultural understanding is there's still a gap between English and other countries in multimodal models. So now I'm going to cover two papers that we worked on in terms of trying to reduce this gap during training. So the first one is a simple approach that basically just translates data that is available in English, multimodal data is available in English, into our target languages. In this case, we use the 20 languages available in Glue to double check what is the performance that we can get by doing this very simple approach. So we translated the pre-training dataset that we use at that time, which is conceptual captions, which consists of roughly 3 million image text pairs, into the 20 languages in Igloo by using the M2M open source machine translation model. When we did these translations, we found some typical type of errors that the machine translation model made. The first one was that of repeating tokens over and over. So here's an example for Swahili, where the model just generates these two words, mifano ya, in perpetuity. And the second issue that we found is that sometimes text in English was being copied in the target language. So the way we approached this was to deploy two very simple statistics to find these bad cases. The first one, to find repeated tokens, we use the type to token ratio as a measure of the diversity of the caption. And for tokens that are being copied from the source language, we simply used sentence blue score, where we checked what is the overlap, essentially, between the target and the source sentences. We then looked at some of these examples manually to identify what are the different thresholds that we should apply to different languages. And interestingly, we found that we could easily group these languages by script and find a single threshold for each of these two groups that would work well in terms of filtering out most of this poor data. And we saw specifically that some languages like Japanese, Korean, Tamil were the most affected by this M2M model. We then trained a version of this X-Uniter model that I talked about before on this data, and which we call TDMML, and found that this approach, this very simple approach, actually helps boosting performance on every task in Igloo. After our work, there's been like more papers in terms of training multilingual, multimodal models. One of these is this ClickOT approach, where the authors start from a vision language model that's been trained only on English data, and then they take a multilingual text encoder that has never seen vision and fine-tune it to match the representations given by the text encoder from the English multimodal models. And so after this training is done, the authors can simply plug in this multilingual text encoder with the original multimodal-based visual encoder to perform multilingual multimodal tasks zero-shot. And another interesting approach was that of CCLM, where the authors take different languages as different modalities. So by using this multi-view approach, they just try to make the representations in the image encoder similar to representations of a given language in the text encoder, as well as the representations, as you can see on the right, of parallel sentences from the same text encoder, similar and close in the semantic space. And next, I'm going to present this work on cultural and socioeconomic diversity in contrastive models. As I said before, we sometimes have approaches that work on multilingual and multicultural data, but in this case, we also look at the cultural aspect per se by removing the multilinguality effect. So one thing that people do when they train these dual encoder contrastive models is to filter out data that is not in English. So this is typically done by many of the approaches that you see online. And our claim here is that this is a bad pre-processing step, and that actually we can achieve better representations, better visual representations, if we train the models on all the data we have available. So you can see here on this example of this tower on the left, that a model was only trained on English data would categorize this tower as being the CN Tower in Toronto rather than being the Milad Tower in Iran. We study this sort of training through different setups. We have a setup where we only use English-only data. We also have then a setup where we use only global data. That is data that is in English as well as multilingually. And finally, we have this GlobeTL, where we translate multilingual data into English. And the first result that we have is that using English-only data exacerbates the socioeconomic disparities that are already available in our culture, in our world. So if we train a model on English or global data, it doesn't really affect performance on high-income households. On the other hand, the gap is much, much larger when we look at images that come from houses with a lower income. And second result that we had in this paper was that we can easily adapt global models to Western data, but not vice versa. So this is a bit of a complicated plot, but essentially what we have here are training curves. So we have evaluation performance on ImageNet as we train the models over our budget of training. And you can see here that the English model in yellow performs best, and the model was trained on global data in blue performs much worse. However, what we can do is in the last part of training, we take the global model and fine-tune it on English-only data. So this is the representation in green. And you can see that basically at the end of training, we can match the performance of an English-only model. On the other hand, if we try to do the opposite, where when evaluating on cultural benchmark, such as GLD, then the model that was originally in English, yellow, when we start fine-tuning on global data, and this is the orange curve in the plot, then on the right plot, then you see there is a big gap in performance between the global model and the model was in English and then fine-tuned on global data. And this sort of multicultural training has also been shown to be effective across different papers. This paper from Wen and colleagues at NeurIPS last year, where they show that essentially multilingual data can be translated into English, and as a benefit of this, one of the benefits you obtain is to have more diversity in the visual representations. And also, it's also been shown that if you scale up the amount of data, so there's this new data set, Webley 100 billion, the performance really improves across aspects such as multicultural and multilingual performance, rather than the standard Western benchmarks that we are used to. All right, in the next 5-ish minutes, I just want to touch upon generation, which is a topic I've been working on in the last year and a half. So visual generation from text. I personally haven't been working on the multicultural aspects, but I think there's some interesting work going on. So I just wanted to touch upon some interesting papers that I came across. First of all, if you're not familiar with text-to-image generative models, this can be trained in 2 different ways. One is autoregressive models, and the other type of family is diffusion flow models. Nowadays, most of the models are latent. So by latent, we mean that given a visual representation like an image, we can encode it with some sort of tokenizer. Here's typically like a VAE, and then use these tokens to model the visual space. In autoregressive models, it's exactly like in language models. The model is trained to predict the next token that comes from this tokenization step, one after one. In diffusion, it's a little bit different, where the model, in addition to the caption as an input, also takes a timestamp and some sort of noise. And then the goal is to denoise these original representations through multiple steps until you obtain the final representation that can then be used by the decoder and the tokenizer to map back to the visual input. So talking about work in this direction, multicultural aspects, there is this benchmark called CUBE, where the authors try to collect cultural concepts from a knowledge base. So what they do here is they identify some sort of high-level categories, such as cuisine and landmarks, and then they traverse a knowledge graph, like Wikidata, to find entries that are potentially relevant for a given culture. And finally, they use an LLM to refine this selection. The authors evaluate 2 types of multicultural competence. The first one is awareness. So see if the model actually knows some of the concepts that are from different countries. And the second one is diversity. So given a high-level definition, such as Italian cuisine, how diverse are the generated images? And so this is how the models are evaluated. For instance, for cultural awareness, given some sort of artifact name, such as sushi, then human raters evaluate faithfulness and realism. And overall, the authors show that 2 of the models that were performing really well at the time are far from perfect, especially with respect to faithfulness for regions that come from the global south. And in terms of diversity, they find the 2 models that they evaluated have different strengths. So some models do better in some categories, such as cuisine, and others do better in other categories, such as landmarks. But overall, they've really failed to capture the breadth of cultural diversity. And finally, I really like this paper from Kanuja and colleagues on image transcreation for cultural elements. So transcreation is the task of translating content from a source to achieve the same effect on a target audience. You can think of this in the text space as translating idioms. So we don't typically translate word by word, but we adapt what we mean to the target audience. So they introduced this task for multimodal models, where even in the visual space, there is some sort of transcreation happening. So an example here is from this Inside Out movie from Pixar, where the kid was shown to dislike broccoli in the US version, but instead broccoli was replaced by bell peppers in Japan. Or like here for this advertisement by Ferrero, where this basically Christmas tree was converted to a kite for Chinese New Year in China. And the authors here collect two types of data set. One is based on specific concept, and another one is more about applications. So in this case, for instance, you can have applications such as education and literature, where showing common objects in the speaking population helps kids learn some sort of arithmetics or other education tasks more easily. So for instance, here, while you could use cherries in the US to learn about counting, you could replace them with cherry blossoms in Japan. They evaluate different image editing models in this paper. I'm not gonna go through the details now, but we can talk about this during the Q&A. But essentially what they find is that for some of the countries, even just transcreating specific concept is really hard. So only 5% of images might be transcreated successfully. And moreover, when you look at this harder application data set, such as education and literature, then none of the models as of last year were able to perform this task. All right, so this brings us to an end. Essentially, what I've tried to talk about today was giving you a little bit more context about the challenges and the progress that we've been making in multicultural multimodal models. From an evaluation point of view, we saw that there's a clear gap between English and multimodal performance. The gap has been reduced over the last 2 years, but it's still relevant and significant. There's also like an increasing number of papers on benchmarking multicultural understanding, both in text-only NLP as well as in multimodal NLP. And I think it's also important to think about how can we create benchmarks, tasks that are useful for the different populations. So some of these benchmarks are on generic tasks that could be used to evaluate multimodal performance, but it's also important to think about what are the real use cases that different populations have for AI models. And more generally, I also think we have gained a lot of tools and expertise in comparing different models as we develop them. But this is not necessarily the case for benchmarks. I think it would be really cool if we could try to better identify similarity and differences between benchmarks so that we can create complementary data sets to evaluate our models. In terms of training, we saw that high quality multicultural data is scarce and usually results in subpar quality of the models trained on this data. And so I think it is also interesting to think about what kind of large scale data can we find so that it would also help multicultural awareness. And are there scenarios where this sort of adaptation of multicultural, these capabilities of multicultural knowledge are not just some sort of fix that we do after we pre-train our models? We actually been working on a data set in this aspect to try to collect multicultural image caption data. It's been going on for 2 years, and I think we're almost ready to launch the campaign to collect the data. So please stay tuned. And finally, on the modeling side, there's a clear gap that different papers have found between proprietary and open source models. And so I think it's interesting to try to figure out why are open source models falling behind? What are we missing from these models to match the performance of proprietary models? And finally, how can we actually distill these local cultures efficiently into existing models? So let's say we have one of these big models that work very well across different tasks. How can we easily adapt it to different cultures? And Yep, this is everything I had. Thank you.
Thank you very much, Emanuele. Very, very interesting talk. And yeah, so we will start with the questions. If anybody has a question, please. So if someone has a question, you can just switch on the microphone and ask freely, okay? Okay, so I have one question for you, Emanuele. And it turns out that I had to look at a paper about a cultural benchmark, but it was only a text-only benchmark. But it was quite interesting for me to see that reasoning models were performing better than, let's say, normal language models, usual language models. So I had that question that, as this benchmark was about knowledge, factual knowledge retrieval, how could a reasoning model improve the performance of a base language model? Because it's just having that knowledge, no? And it turns out that some of the generations of those reasoning models were showing that, yeah, they can somehow, yeah, reason about some cultural clues and infer better the answers, no? So my question was, do you think that those new reasoning approaches could be a good way to adapt, let's say, base multimodal models to cultural diversity and even cultural, I mean, even different languages?
Yeah, I think this is actually like a good suggestion. Like, I think like we've been struggling to get out of all of the knowledge that like language models have in their parameters. So I don't know if you follow the literature. There's different type of sampling we can do. Besides greedy, we can do toppy, we can do different type of parameterization. And I think these are just showing that there's a lot of knowledge inside these models that we cannot easily extract with our sampling strategies today. So I think like reasoning allows you to explore this space more thoroughly at the expenses of a like lower, like higher inference cost. And I think, yeah, it could be like an interesting aspect to look into. Like if we can get these reasoning traces, how can we distill them into the base model so that it can adapt to the culture more quickly, right? Like there was like at some point we worked on like factual knowledge in multilingual models, and essentially like the language that you prompt the model in affects the performance of the model. So if you, for instance, if you ask for the capital of a given country, if you ask, for instance, in French, what is the capital of Japan, it might be the case that the model predicts Paris, just because there's this overlap between the language and the culture. And so I think it would be interesting to see if we can use reasoning traces, even if they're in English, and then see if we can make multilingual models also improve multicultural performance.
Yeah, I was wondering about that also because, as you said in your presentation, gathering multicultural and multimodal data is very difficult, and I don't see an easy way to collect that kind of data in the scale that we need for those huge models, no? So maybe we have to think some other ways to adapt current models to different cultures, different visual symbols, these kind of things. And I don't know whether maybe reasoning or something like that could be a way for that.
Yeah, I think this is like the point I was trying to make, that now this is like, we've seen that these models, whether we like it or not, improve a lot when trained on large scale data. So one way we could try to approach this sort of problem is that, okay, we know these models work well on large scale data. How do we gather large scale data for the things we care about? And I think this is an interesting research question. It doesn't necessarily involve a lot of compute. We can think about how do we gather this data? What are the things we need to do? And we can show some sort of low resource, low scale approach that works. And then big labs can pick it up if they find this interesting. But I think having something that can scale and gather this like multicultural knowledge is hard to think of, but it could be really rewarding.
Yeah, I agree. Thank you. Is there any other question? Well, it seems we have some shy participants here. Okay, we had a message here. Let me check. Okay. Okay, so it seems we don't have any other question. So thank you very much, Manuel, for your interesting talk. And I think it's a very interesting research topic, and yeah, very applicable. So yeah, keep on there, and we will see each other soon. Thank you very much, and thank you all the participants also.